In this video, I want to talk about what your book calls optimization problems, making something as big as possible or as small as possible, what I sometimes call an applied max-min problem. And I think the best way to illustrate the idea of the question and the solution method is just by doing an example. So, say we're given let's make it 8 foot by 6 foot rectangle of cardboard. So we start off with this big piece of cardboard, 8 feet long and 6 feet wide. And what we want to do is to fold it into a box with no top. So it'll have a bottom and 4 sides, but no top, no lid. So we want to create a box with no top by cutting squares from the corner. From the corners, I should say, 4 corners, and folding up the sides. So in our original rectangle, we cut a square out of this corner, a square out of this corner, a square out of this corner, and a square out of this corner, and that leaves us with 4 flaps that we fold up. The middle part becomes the base of the box, and the 4 flaps become the 4 sides of the box. And the problem is, the question is, find the dimensions of the largest volume box that we can so create. So we start off with a rectangle. We take scissors and cut out squares from the 4 corners, leaving us with 4 flaps, like a plus sign, and then we fold up the sides. So let's take a look at how we would solve a problem like this. Step 1, and this probably doesn't come as a huge surprise in light of some things we've been doing recently, draw a picture. So let's start with our 6 foot by 8 foot piece of cardboard. So this side, the short side, will be 6 foot, and the long side will be 8 foot. So it's 6 foot from here to here, and 8 foot from here to here. What we're going to do is take scissors and cut a square out of this corner. So we will just take our scissors and cut, and remove this entire square. And we will remove another square over here. So that's gone. And another square over here. And another square over here. And that leaves us with something shaped like a plus sign. Once we do that, we really, if you look at this, we basically have this middle rectangle and 4 flaps. We can take each of these flaps and fold it up so it is perpendicular to this middle section. And these 4 flaps become the 4 sides of our box, and this becomes the bottom of the box. And of course, as I said originally, there is no top of the box. So we have 4 flaps which become the four sides, and the bottom of the box. I hope everybody's okay with that. And what we want to do is find the largest in terms of volume box that we can form. So what we have control over is only one thing, how big these squares are. Now I think you can see that if we want our box not to be wonky, each of these things has to be a square. We couldn't cut out a rectangle. If this side was, say, longer than this side, then this would fold up higher than this. The two sides wouldn't meet. And these four squares would all have to be the same size, or this thing is these won't be like rectangles. The sides won't be rectangular. It won't be a nice rectangular box. So all we have control over is how big we cut these squares. If we cut really tiny squares, let's say we just cut the squares that big, then we have a box with a really big base. But it has almost no height. And so in terms of volume, it's not going to be a very big box. If we cut these squares fairly large, let's say I cut that first square kind of like this, and that second square over here, and the third square over here, and the fourth square over here, you can see that now we have a big height. That height that we cut out is pretty big. But the base of the box is really tiny. So you couldn't keep much in that box. So if we make the squares that we cut out either too big or too small, the box is going to be not going to have a large volume. It's going to have a small volume. Somewhere in between the too small and too big is this number, the size of that square that we can cut out, that will give us the biggest volume box, and that's what we're trying to find. Step 2, I bet you can guess what step 2 is based on some problems we've already done in this course. So step 2, define variables. So step 2, let's define some variables. So one thing we have control over, the thing we have control over is how big each of these squares is. So if we just call that length right there x, which means that's x, which means that's x, and that's x, and that's x, and that's x, all these, since these are squares, and they're all the same, once we decide on one of those x's, they're all the same. That's one thing, that's what we have control over. That's going to be one of our variables, the thing we have control over. The other variable is going to be the thing we're trying to make as big as possible or as small as possible. In this case, we're trying to make something as big as possible. That thing is the volume. But that might be hard to illustrate on my picture, so I'm just going to do that right here. V equals volume. I'm not going to make it fancy. V equals volume. Done. I've defined my variables. I've drawn my picture. Step 3. Write a formula for the thing you're trying to maximize or minimize. So write a formula for the thing you're trying to make as big as possible or as small as possible. In this case, the thing we're trying to make as big as possible or small as possible is volume, and we're trying to make it as big as possible. So we want the volume to be as big as we possibly can make it. So V equals, we want this, what's on the other side, to eventually be all in terms of x, because x is our other variable. That's the thing we have control over. So V is volume, it's going to be something in terms of x. Let's just take a little while to get there. There's no need to rush this. We know that the volume of a box is the length times the width times the height. Let's see if we can figure out what the length and the width and the height are, all in terms of x. So the length of this box, once we fold up these two ends, is going to be the distance from here all the way over to here. We've lost this amount on this end. We've lost x on this end when we fold up this side. We lose x on this side when we fold up this flap. And so we started off with 8 feet but we lose an x and we lose another x. So before I write it down on the blackboard, see if you can figure it out for yourself. How long is that box? A formula in terms of x? Well, it was 8 feet to begin with. So 8 minus 2x. And that's the length of the box. 8 minus 2x. Now we need the width of the box. How long is it from here to here? How wide is that box? Again, feel free to think about it, pause the video, do whatever you want to do. How wide is that box? Well, it's the whole piece of cardboard. Started off at 6 feet, you lose x over here, you lose x over here. So the width of the box is 6 minus 2x. And how high is that box? How high are each of these walls? Well, they're just x. You can see that what we have over here is nothing more than a function of x now. All I'm going to do right now is a little bit of algebra. I'm going to multiply this out. By the way, I could just call this v of x just to emphasize that x is our independent variable there. V of x, however you like it. So if we multiply this all together, we can FOIL this out. And again, you can do this in your, you can pause and do it before I get to it. Let me do the x squareds first. So minus 2x times minus 2x is 4x squared. Minus 2x times 8 is minus 16x. Minus 2x times 6 is minus 12. Minus 16 minus 12. I guess that's minus 28x. And then the 8 times 6 is positive 48. The x is still there. Sure wish you guys were here to help me catch mistakes. 16, 12, that looks right. And then we multiply the x in. We have 4x cubed minus 28x squared plus 48x. So that's my v of x. I'm just going to rewrite that over here. That's the thing I'm trying to make as big as possible or as small as possible. Step 4. And step 4 is a step that people often leave out, so make sure you don't leave it out. Write an interval for your independent variable. Write an interval for our independent variable. X goes from here to here. X couldn't possibly be smaller than this, and it couldn't possibly be bigger than that. I am going to write this as a closed interval. And I'll explain after I write it why, since you could argue that it might make more sense as an open interval. And if you did, I would certainly accept your argument. But let's treat it as a closed interval. What's the smallest that x could possibly be? X is a length here. Could x be minus 1? Could I cut out a square of side length minus 1? That doesn't make any sense at all. Minus 1/2? The smallest number that makes any kind of sense is 0. And you could even argue that 0 doesn't make any sense. If I cut out 0, I basically cut out no squares at all. And then the whole box is the bottom and it has no height at all. But at least it makes some kind of sense. So 0 is the smallest x value that makes any kind of sense. Now let's see what the biggest x value is that makes any sense. If this side is length, this whole side of the box is length 6, if I cut out, a 1 by 1 square over here, 1 by 1, then I started off with 6, I lose 1 over here, I lose 1 over here, and so this would be length 4. I could cut out 2 and 2, and that would make sense. If I cut out 3 and 3, these two squares would touch. Right? If I go 3 down from the top and 3 up from the bottom, now they touch. If I cut out squares like that over here, basically what I've done is I've cut out what happens is I just have this little rectangle here, and I fold like that, and I have not a box, but like an envelope. It has no bottom. It's just all side. And so the biggest thing that makes any kind of sense is 3. After 3, these two squares would overlap. That doesn't make any sense. So the biggest this could possibly be would be 3. Okay, so we're going from x equals 0 to x equals 3. If there was a part of this that confused you, based on my past experience, it was this. So take a look at this. Now, I told you I would tell you why I decided to go with a square bracket rather than a round bracket, round parentheses. And that's this. What I have here is a continuous function, and if I use square brackets, I have a closed interval. We have a theorem, which we studied much earlier in the course, called the extreme value theorem, where if you have a continuous function on a closed and bounded interval, you know for sure that function has a maximum and that function has a minimum. And we also have a technique for finding it. You remember the technique. So right now, let me just recopy my v of x over here. V of x equals 4x cubed minus 28x squared plus 48x. And my interval is 0 to 3. This is an x interval. X is at least 0, and it's at most 3. And what we're going to try to do is find x to make this as big or as small as possible. Let's not forget what this is. For any x you care to give me, this formula tells me the volume of the box that we make. So I think I can erase what's over here now. So I'll leave the v equals volume on the board there, but I'm going to erase this. So what are we up to now? That was step 1, step 2, step 3, step 4, step 5. Solve the max-min problem. So we have already done this many times. We have a problem with a continuous function at an interval. We want to solve the max-min problem, solve the optimization problem, if you want to say. So let's go ahead and do that. We know what to do. We're going to take the derivative. We're going to set it equal to 0 to find all the critical points. We'll discard the ones that are not in the interval. Then we'll plug the remaining critical points plus both endpoints into the original function. So let's go ahead and take the derivative. V prime of x equals 12x squared minus 28 times 2, I guess, is 56x plus 48, assuming I haven't made any mistakes. And we'll set v prime equal to 0. So we are on familiar territory now. So we have 12x squared minus 56x plus 48 equals 0. Those numbers are huge. I think I'm just going to divide everything. What's the largest thing which divides 12 and 56 and 48? I am guessing 4 is the largest thing. So if I divide everything by 4, if I divide both sides of the equation by 4, 12 divided by 4 is 3. 56 divided by 4 is what, 14. Yeah, and 48 divided by 4 is 12. Now let's solve that. We could have just as easily solved this. You can put this into your calculator if you'd like decimal values. I'm just going to use exact values for now. If you don't like exact values, please feel free to use decimal values. So x is equal to negative b, so that's 14 plus or minus the square root of b squared, that's 14 squared minus 4 times 3 times 12 over 2 times 3. And so this equals 14 plus or minus the square root of 14 squared is 196, and this is 12 times 12, that's minus 144, all over 6. If you don't like this, if you don't like doing the exact numbers, get decimals, I don't care. It's all good. So 14 plus or minus the square root of, let's see, 44 to 94 would be 50, so this is 52 all over 6. So let's see, I guess we can simplify that just a little bit more. 14 plus or minus, let's see, root 52 is 52 is 4 times 13, so this is 2 root 13 all over 6, and we can simplify this a little bit more as 7 plus or minus root 13 over 6. Okay, those numbers aren't particularly nice. If you want decimal values, that might look nicer. All right, so let's see which of these is in the interval and which ones aren't. They might both be in the interval. Neither one may be in the interval, but let's take a look. So this is really two numbers. This is 7 plus root 13 over 6, and 7 minus root 13 over 6. So 7 plus root 13 over 6, root 13, oh sorry, this should be over 3. I forgot, I divided the top by 2, I should divide the bottom by 2. So these should all be 3's. Root 13 is certainly bigger than root 9, so this is bigger than 7 plus 3, that's bigger than 10 over 3, that's bigger than the largest value. This is bigger than 3. If you type this into your calculator, you will find this is bigger than 3, we get rid of this. 7 minus root 13 over 3, this is going to definitely, what the numerator is definitely less than 9, so we divide by 3, this is definitely between 0 and 3, so we keep this. So now what we're going to do is we are going to take this critical point, so 7 plus root 13 over 3, and both endpoints, and plug them into my v of x. So this is x, and we'll compute v of x. If we plug 0 in, we're definitely going to get 0. If you plug 3 in, you can see what you get. You get 4 times 27 minus 28 times 9 plus 48 times 3, and that all cancels out and gives you 0, which you knew already, because if you cut out a square of 3 by 3 and 3 by 3, this box has no width. So length times width times height, as soon as one of those is 0, it's going to give you 0. The only one that's going to give you a positive number is this, and I'll spare you what you get when you plug that in, just because the arithmetic would be terrible. If you're using decimals, it's going to look a lot easier if you plug it into your calculator, but this will be a positive number. Now, I asked what was the dimensions of the box. So, dimensions, I want length and width and height. So step 6, answer the problem. I want to make a big deal of this because so often people do all the hard work and then they forget what the question actually asked. If I asked what was the volume of the largest volume box, you would just give me the number here, whatever number was here. But I asked you for the dimensions, length, width, and height. So make sure you go back to the problem and read what it is you're supposed to answer. So the length, the width, and the height. Well, the height is just x. That is just 7 minus root 13 over 3. And that's in feet. And the length is, we know, is 8 minus 2 times this number. Now I imagine the first question you're going to ask is, do I have to simplify that? No, I suspect most of you are going to want to work in decimals anyway. So once you've done it in decimals, there's no simplification necessary. And the width is 6 minus 2 times 7 minus root 13 over 3. Remember where the 8 minus 2 times x came from and the 6 minus 2 times x came from? That's already erased, but when we wrote out the volume of the box, those were the length and the width and the height. And, feet. And this is our answer. If I went through all this hard work and gave the largest volume box that I could possibly get, I wouldn't have answered the question. And and if somebody was grading my work, they wouldn't be able to give me full points. So make sure, step 6, it's the easy part. Once you've done all the hard stuff, go back and answer the question. I want to point one more thing out. Notice that these aren't whole numbers at all. There's nothing that guarantees that the largest box has to be when you cut out a square of size 1 or a square of size 2 or even something like a half. It could be totally irrational, something you would never guess. And so you can't do this by trial and error. You have to go through and actually do the calculus to figure out where the biggest and the smallest or the smallest value is.